Hey, welcome to the last session of the day. Our next speaker is Stefania Damato, who will be specifying quotient inductive types using containers.
Thanks for the introduction. So, today I'll be talking about specifying QIITs using containers. And this is ongoing work with my supervisor, Torsten Ottinker. So in this talk, I will be outlining the problem that we're trying to solve, describe some conjectural results that we have, and also talk about some approaches that we're thinking of taking going forward. So first of all, I want to start by illustrating what quotient inductive types are. So as the name suggests, they're a combination of two ideas. So first of all, we have quotienting. So we have we can define inductive types not only using point constructors, but also using path constructors. And so we can use equalities in our definitions, but these equalities are set truncated. So we don't have any non-trivial higher equalities, and in a way these are higher inductive types, but they're not very high. And then the next part of this definition is that we also allow induction. So this means that we can define a type A together with a type family B over A, and these are defined simultaneously. So the definition of B can obviously depend on A, but crucially, the definition of A can also depend on B. So I can define a type A while referring to the type family B, which I'm also defining simultaneously. And I've given an example here of a very simple type theory, which has two sorts, con and tie. So con is the type of context, and then tie is a family over con, which is the type of types over contexts. And notice that we have implicit set truncation here by the use of set. And this definition consists of an empty context extension. I'll get to each in a second. And then for types, we have the base type, which is well typed in the context. And then we have the sigma type. This each constructor here, notice that it's an equality constructor. And this is saying that if I extend the context gamma with A and then extend that with B, that's the same as if I were to extend gamma with the sigma type of A and B. And so the quotienting is happening by this inclusion of eq, which is an equality constructor. It's an equality on con. And the induction allows us to, for example, talk about sigma here in the definition of con, where sigma is a constructor of time. So these are quotient inductive types, and what we'd like to do is to have a theoretical understanding in a similar way that we have for other classes of inductive types. We see this as a starting point towards the syntax and semantics of higher inductive types, but also they're interesting in their own right. There's a lot of interesting examples of QIITs. And so the situation for other classes of inductive types, so specifically ordinary inductive types like the natural numbers, lists over A, binary trees, and so on, and also inductive families, so the type of finite sets, vectors. These two classes of inductive types, we have a very good theoretical understanding of them. So we know how to represent them via endofunctors, and we know how to talk about them semantically as initial algebras of these endofunctors. We know that they have a normal form via containers, and what this means is loosely that we can sort of classify the endofunctors on set, for example, that have initial algebras by saying that these are exactly the endofunctors that are container functors. And then we also have an understanding of them syntactically, because we have W types. So if I have a type theory and I want to add, for example, ordinary inductive types, I can just add the W type, and that will give me all ordinary inductive types. And so this is the situation for these two classes of types. And so we ask, well, what about quotient inductive types? What's the situation here? And so, for example, for this con tie example I've just shown. So the first obstacle is that we cannot even get a representation for quotient inductive types as functors. I mean, this isn't proven, but it seems like it can be done because there's far too much dependency between the constructors. But luckily, we have an alternative to this, and so we can still represent quotient inductive types, but not as functors, but using this iterative process where we start with a category of sorts and then specify the constructors one by one until we get a category of dialgebras. So I'll outline this process here. So first, we start with a category A0 of sorts. And so, for example, if I want to define this example, the category A0 would have objects which are pairs. And the first object being a C of type set, and then the second one would be a family T over C, so T of type C set. And so A0 stands for the sorts of the quotient inductive type. And then what we do is we start adding constructors one by one. So the end constructor is specified by two functors, ln and rn. Ln stands for the left-hand side of the constructor, or the arguments to the constructor, and then rn is the target type. And this integral here, this integral ln is just the category of elements over ln, and so it's just an object of an and then ln of that object. And so again, if I were to, let's say, be specifying this context extension constructor, then the left-hand side would be gamma and A, and then the right-hand side would be the sort con. But this also works for equality constructors. So even if I was specifying eq, then the right-hand side would just be this whole equality. So this is how I specify a constructor. So I start with A0, I add one constructor, and then what I do is I obtain this new category of dependent dialgebras. And this has objects which are pairs. So we have something of the previous category. So in the first step, it would be A of type A0. And then we have this constructor that we've just specified. So it would be going from the left-hand side to the right-hand side. And then morphisms are again morphisms in the previous category, such that these C and C primes act in a way that they're the A and A prime components of this natural transformation between ln and rn. But the basic idea here is that this process works by first having this category A0 of sorts, adding one constructor, getting a new category, adding another constructor, obtaining a new category, and so on and so forth until we've added all the constructors and we get one last category of algebras here. And then the quotient inductive type we're representing is obtained as an initial object in this category. So now, thanks to this process, we can go back to this table and fill in some of the question marks. So now we have a representation for quotient inductive types as a sequence of functors ln and rn, one for each constructor, and also a sequence of categories of dialgebras. And we also have categories tier semantics. So again, we have an initial algebra semantics on quotient inductive types. The current problem is that we still don't have a good understanding of these last two columns here. So what we would like to have is something similar to containers, but for quotient inductive types. And also we'd like to have a syntactic understanding of quotient inductive types, similar to what we have here. And so what we've been thinking about is that we conjecture that we can get something similar to these here by restricting these ln and rn to be what we call generalized container functors. And also we want a universal type here, which we call a QW type. And there have been some attempts at this by some other people. So there's a paper by HoTT-UF and Fiore and Steenkamp. where they obtain something like this using the whisk axiom, which is like a weakening of choice, which is widely accepted in the constructive community, but we think that we can maybe do without it, or at least want to look into this. And then there's also another paper by Kaposi and Kovacs and Altenberg, where there is such a type, but first of all, it's quite a big type. We want quite a succinct type, just like the W type. And second of all, it doesn't, at least in this paper, it doesn't deal with infinitary constructors, and so it's not general enough. So going back to the box here, so our conjecture is that if we require Ln and Rn and to be generalized container functors, plus we have some other restrictions on the right functor, then we are able to get a normal form for quotient inductive types. And by this we mean that we are guaranteed an initial object in the last constructed algebra in that process that I described. And I've written down the definition of a generalized container and a generalized container functor. This is because in the current literature, containers aren't general enough to cover functors of these types. And so we need a new definition. And this was proposed in an abstract by Altenberg and Kaposi. And so this is the definition I state here. But basically the idea is that it will give us something similar to what containers do for ordinary inductive types. And so to illustrate the situation that we have at the moment, so yeah, so this iterative process works by first having a category A0 of sorts, specifying L0 and R0, and obtaining A1, and then adding so on until we get to this last category AN, which is the representation of the actual quotient inductive type. Now, these forgetful functors always exist, so I can always obtain these UNs. But what we'd like to do in general is have a general way of writing down these FNs, which are left adjoints to these UNs. And the reason is that if we have these FNs, we can then compose them into this big F, going from A0 to AN. And if this is a left adjoint to U, then we know that left adjoints reserve co-limits, specifically initial object. So if there's an initial object in A0, then we can guarantee an initial object in AN. And there is this result, I believe by Jumilo, which states that A0 in its highest generality can just be the category of families over set. And so that has an initial object. So if this is in fact a left adjoint, then we can guarantee an initial object here. So what we're looking for is basically an existence result for an initial object here. And so one approach to this is to try to get a definition of these FNs via the adjoint functor theorem. So all of these categories have been shown to be complete in this paper, quotient inductive types. All of these U's are also continuous, so we are guaranteed to have a left adjoint if the UNs obey the solution set condition. And so this is one approach that we're looking into, where basically we want to ask, is the restriction that we've mentioned before of having generalized container functors enough to impose the solution set condition on these UNs? There's also some other variants of the adjoint functor theorem. So there's some work by Adamek and Lambeck, who talk about locally presentable categories, which they have a large set of objects which can be approximated by a small set of objects via filtered co-limits, and they have adjoint functor theorems for those categories as well. And so we're also thinking of looking into that. Another approach would be to perhaps look at these categories as type theories and see whether they themselves have W types as type theories. And so that is another possible approach that we're looking at. But yes, the point is here that we would like to guarantee an initial object in the end. And so in conclusion, we said that quotient inductive inductive types combine set truncated inequalities with induction induction, and we can represent them semantically as initial diagonals. We conjecture that if we restrict the left and right functors for constructors to generalized container functors, then these correspond to exactly those categories of diagonals with an initial object. And then we're still trying to answer this question of what does a universal QW type look like? And we want a very succinct, or at least as succinct as possible, such type. And so yeah, that's it from me. Thank you very much for listening.
Are there any questions?
Thanks for the talk. Okay, wonderful. Yeah, I'm not really familiar with containers, but if I interpret it correctly, do you mean it like no, in the normal inductive data types, they correspond with like the polynomial functors, or?
Yes, also known as polynomial functors. Yeah, so they're the type here equivalent to polynomial functors.
Okay, and do you expect to have some, let's say, like the polynomial functors that are, since they're like built up in a, let's call it in since let's say there is a concrete description for polynomial functors, do you also suspect something like, well, to hold analogously for these generalized containers, or?
Yeah, so this is a generalized definition of the normal container functors, which we use for ordinary inductive types and inductive families. And so this is a slightly generalized definition. In particular here, we usually have just errors in set, whereas here we have homomorphism in C. So yeah, this is kind of the analogous, I guess, container to what you're saying.
Yeah, thanks.
Any other questions? I had maybe a question, but I'm not sure to what extent it actually applies. So I was wondering if anything, but I'm actually not sure if the result is presently there. Like, is this work in progress, or is the?
It's work in progress, yeah.
Yeah, what I wanted to ask is, like, could the result be formalized in a language, like in type theory as it exists, or would you need additional stuff? Because like many treatments of QIITs are not that easy to formalize. So I was wondering.
Yeah, so this is currently something that we're looking into. So yeah, it seems like we can obtain QIITs using choice, but we don't.
Yeah.
We want to try to avoid that as much as possible, but yeah, we might need, for example, to use valence or something like that. But it's something we're looking into.
And so, I mean, the way you need something like a QW, you know that fits the way and not conservatives. You need some text such.
Yeah. Right. Yeah. Then let's thank the speaker again, I think.